Welcome to Review Central's Mathematics Proficiency Reviewer Drills, featuring drill questions on logarithms and logarithmic identities. Mathematics proficiency is a typical subtest in many exams, including most high school and college admission and scholarship qualifying tests, some professional licensure and certification exams, and even some employment pre-qualifiers. If you are eyeing or are set to take any of these tests, then this reviewer is intended for you. There are 16 carefully curated questions featured on this reviewer. All questions are modeled on actual questions that appeared on various mathematics proficiency subtests. Before we proceed, don't forget to subscribe to Review Central and click or press the bell button to make sure you get notified whenever we post a new reviewer or other review materials on this channel. Let's begin.
Drill question number 1. Which of the following is the logarithmic form of 7 raised to 5 equals 16,807? A. Logarithm base 7 of 16,807 equals 5. B. Logarithm base 5 of 16,807 equals 7. C. Logarithm base 7 of 5 equals 16,807. D. Logarithm base 5 of 7 equals 16,807. E. Logarithm of 5 over 7 equals 16,807. The correct answer is A. 7 raised to 5 equals 16,807 and logarithm form is logarithm base 7 of 16,807 equals 5. Recall that a logarithm is just an exponent. To be specific, the logarithm of a number z to a base x is just the exponent, y, you put onto x to make the result equal z. That is, x raised to y equals z is equivalent to logarithm base x of z equals y. This is the very definition of a logarithm. If we understand this, then we understand logarithms. From here we can see that any exponential equation can be transformed to its logarithmic form, and vice versa. Going back to our given equation, we can determine the values of variables x, y, and z from our given exponential equation as follows. X equals 7, y equals 5, and z equals 16,807. We then substitute the values of variables x, y, and z into the equivalent logarithmic form of the equation. Therefore, 7 raised to 5 equals 16,807 in logarithmic form should be logarithm base 7 of 16,807 equals 5. A logarithm question in a mathematics proficiency test cannot get any easier than this, because this involves the most basic concept in logarithms, that a logarithmic function is simply the inverse of its equivalent exponential function. Having said that, if you had difficulty answering this question, then you really must take a serious refresher course on the topic of logarithms. The good news is, if and when a logarithm question does appear in your mathematics proficiency exam, there's a very good chance that it will be as simple as this. Now let us give you our very first Review Central Pro tip for mathematics proficiency problems involving logarithms. Always remember that a logarithm is just an exponent, and memorize the equivalent exponential and logarithmic equations that define this relationship. That is, any exponential expression can be transformed to its logarithmic form, and vice versa, as follows. X raised to y equals z is equivalent to logarithm base x of z equals y. Take note that x, y, and z may appear as different variables in other books or materials, including in some logarithmic problems featured here in Review Central. You shouldn't have any trouble recognizing the above equivalent equations regardless of the variables used. Specifically for this drill, and in subsequent mathematics reviewers involving logarithms that we will feature, we will be using the x, y, and z variables. We like to use x, y, and z as they are so much easier to memorize and use. Now we'd like you to read again our equivalent exponential and logarithmic equations several times until they are imprinted in your memory. Repeat after me. X raised to y equals z is equivalent to logarithm base x of z equals y. X raised to y equals z is equivalent to logarithm base x of z equals y. X raised to y equals z is equivalent to logarithm base x of z equals y. X raised to y equals z is equivalent to logarithm base x of z equals y. X raised to y equals z is equivalent to logarithm base x of z equals y. x raised to y equals z is equivalent to logarithm base x of z equals y. Drill question number 2. Write 16 raised to 3/4 equals 8 in logarithmic form. A. Logarithm base 3/4 of 8 equals 16. B. Logarithm base 8 of 3/4 equals 16. C. Logarithm base 16 of 3/4 equals 8. D. Logarithm base 8 of 16 equals 3/4. E. Logarithm base 16 of 8 equals 3/4. The correct answer is E. 16 raised to 3 over 4 equals 8 in logarithmic form is logarithm base 16 of 8 equals 3 over 4. At the end of drill question number 1, we strongly recommended that you memorize how to transform an exponential equation to its logarithmic form, and vice versa. Let's recall that again now. By definition, any exponential expression can be transformed to its logarithmic form, and vice versa, as shown. Going back to our given equation, we can determine the values of variables x, y, and z from our given exponential equation as follows. X equals 16. Y equals 3/4. Z equals 8. We then substitute the x, y, and z values into the equivalent logarithmic equation. Therefore, 16 raised to 3 over 4 equals 8 in logarithmic form is logarithm base 16 of 8 equals 3 over 4. Drill question number 3. What is 1/3 raised to -2 equals 9 in logarithmic form? A. Logarithm base 9 of -2 equals 1/3. B. Logarithm base -2 of 9 equals 1/3. C. Logarithm base 1/3 of 9 equals -2. D. Logarithm base 1/3 of -2 equals 9. E. Logarithm base -2 of 1/3 equals 9. The correct answer is C. 1/3 raised to -2 equals 9 in logarithmic form is logarithm base 1/3 of 9 equals -2. This is essentially the same as drill questions 1 and 2, so let's quickly proceed to solve it. Determining the values of variables x, y, and z from the given exponential equation, and substituting the same into the equivalent equation, we should quickly arrive at the logarithmic form of 1/3 raised to -2 equals 9 as logarithm base 1/3 of 9 equals -2. Drill question number 4. Write logarithm base 2 of 32 equals 5 in exponential form. A. 32 raised to -2 equals 5. B. 2 raised to 5 equals 32. C. 5 squared equals 32. D. 32 raised to -5 equals 2. E. None of these. The correct answer is B. 2 raised to 5 equals 32. This is basically the same as the first 3 drill questions but in reverse. So again, let's recall our exponential to logarithmic equivalence relationship as shown. This time the logarithmic form is given, so we determine the values of variables x, y, and z from the logarithmic equation. We should get x equals 2, y equals 5, and z equals 32. And then we substitute the x, y, and z values into the equivalent exponential form of the equation. Therefore, logarithm base 2 of 32 equals 5 in exponential form is 2 raised to 5 equals 32. Questions in this form appear much less in math proficiency tests than the ones in drill questions 1 to 3, most probably because it is so much easier to transform a given logarithmic equation into its exponential form. We can also quickly validate our answer by checking that the exponential equation is valid even without the help of a calculator. Like in this case, among the answer choices only 2 raised to 5 equals 32 is a valid equation. 2 raised to 5 is of course 2 times 2 times 2 times 2 times 2, which is indeed equal to 32. Drill question number 5. What is logarithm base 1/5 of 1 over 625 equals 4 in exponential form? A. 4 raised to 1/5 equals 1 over 625. B. 4 raised to 1 over 625 equals 1/5. C. 1 over 625 raised to 4 equals 1/5. D. 1/5 raised to 4 equals 1 over 625. E. 1/5 raised to 1 over 625 equals 4. The correct answer is D. Logarithm base 1/5 of 1 over 625 equals 4 and exponential form is 1/5 raised to 4 equals 1 over 625. This is basically the same with drill question number 4, that is, transforming a logarithmic equation to its exponential form. Although logarithmic to exponential transformation questions appear much less than exponential to logarithmic transformation questions in math proficiency tests, when they do appear it will most probably be like this one. That is, involving fractions. Logarithmic equations involving fractions are a bit more challenging to deal with, because it is much more difficult to validate the resulting exponential equations without the use of a calculator. But don't get overwhelmed and don't panic when you see fractions. Just make sure you know your exponential to logarithmic equivalence relationship by heart, and it should be as easy as replacing your x, y, and z variables with the given values. Yes, it is as simple as that. So again, and for the 5th time, let's pull back our exponential to logarithmic equivalence relationship. X raised to y equals z is equivalent to logarithm base x of z equals y. You should have memorized this by now, right? The next steps are just repetitions of the steps from the previous drill question. Get x, y, and z values from the given logarithmic equation, and then substitute these to the x, y, and z variables of the equivalent exponential equation. The correct and final answer should be 1/5 raised to 4 equals 1 over 625.
Drill question number 6. Solve logarithm base 3 of 81. A. 2. B. 3. C. 4. D. 9. E. 27. The correct answer is C. 4. Step 1. Convert the given logarithm into its exponential form, substituting the x, y, and z values taken from the given equation as available. We can see that only the y variable is missing, which is what we are in fact solving for. Step 2. From here, we just need to figure out what exponent of 3 will give us 81, and quickly see that 3 raised to 4 equals 81. In other words, y equals 4. Therefore, logarithm base 3 of 81 is equal to 4. Drill question number 7. Solve logarithm base 2 of 1 over 8. A. minus 3. B. minus 2. C. 2. D. 3. E. 4. The correct answer is A. minus 3. Like in the previous drill question, we convert the given logarithm into its exponential form. We should end up with 2 raised to y equals 1 over 8. Since the result of the exponential equation is a fraction, that is, 1 over 8, what should be the exponent of 2? If we replace 2 with its reciprocal, which is 1/2, we must also replace the exponent y with its reciprocal, which is minus y. Now, what exponent of 1/2 will result to 1/8? That's right, it is 3. Which means that minus y is equal to 3, or y equals minus 3. Therefore, logarithm base 2 of 1 over 8 equals minus 3. Dealing with fractions and negative exponents is a bit confusing, right? Don't worry, with practice you will eventually get the hang of it and soon be able to actually skip step 2. Drill question number 8. Solve logarithm base 1/4 of 16. A. minus 3. B. 2. C. 4. D. minus 4. E. minus 2. The correct answer is E. minus 2. Again, first step is to convert the given logarithm into its exponential form, as shown. Next, if we replace 1/4 with its reciprocal, which is 4, we must also replace the exponent y with its reciprocal, which is minus y. Now, what exponent of 4 will produce 16? It's 2 of course. So minus y equals 2, and thus y must be minus 2. Therefore, logarithm base 1/4 of 16 is equal to minus 2. Drill question number 9. Solve the natural logarithm of e raised to 4. A 1. B 2. C 3. D 4. E cannot be determined. The correct answer is D 4. Step 1. Recall that the base for a natural logarithm, ln, is e. Therefore, we can actually rewrite ln of e raised to 4 as logarithm base e of e raised to 4. Step 2. Convert the logarithm to its exponential form. Logarithm base e of e raised to 4 equals y is equivalent to e raised to y equals e raised to 4. Therefore, y equals 4. Note that an easier method of determining the value of this logarithm would have been to recall the properties of logarithm, or logarithmic identities. In particular, the logarithmic identity. Logarithm base m of m raised to n is equal to n. That is, logarithm base e of e raised to 4 is equal to 4. And we have another Review Central pro tip for you. Memorize this logarithmic identity. The logarithm base m of m raised to n is equal to n. Drill question number 10. Solve logarithm of 1 over 100. A minus 2. B minus 1. C 0. D 1. E 2. The correct answer is A minus 2. Recall that the base for a common logarithm is 10. That is, if no base is specified, we can assume it is 10. Next, we convert the logarithm to its exponential form. The exponential form of the equation should read as 10 raised to y equals 1 over 100. From the previous drill questions, we should already know that if an integer raised to an exponent results to a fraction, the exponent must be a negative number. Since 10 squared equals 100, 10 raised to minus 2 must be 1 over 100. Hence, y must be minus 2. Therefore, logarithm of 1 over 100 equals minus 2.
Drill question number 11. Find the value of z and logarithm base 5 of c equals 2. A. 2. B. 5 over 2. C. 7. D. 10. E. 25. The correct answer is E. 25. This is a very simple logarithm problem modeled on an actual question that appeared on a college entrance test. As you will see, the solution is as simple as applying the very definition of logarithm, the same solution we've been applying in the previous 10 drill questions. As usual, the first step is to convert the given logarithm equation into its exponential form, as shown. In previous drill questions, we've mostly been solving for the exponent y. This time around we are solving for z, since x and y are already given as 5 and 2, respectively. Solving for z is as straightforward as getting the square of 5, which, of course, is 25. Drill question number 12. Which of the following is equivalent to logarithm base x of the quantity, the fifth root of a squared times b, over 2cd cubed? A. 2/5 times the logarithm base x of ab, minus 3 times the logarithm base x of 2cd. B. 1/5 times the quantity, logarithm base x of a squared b, minus logarithm base x of 2cd cubed. C. 2/5 times the logarithm base x of a, plus 1/5 times the logarithm base x of b, minus the logarithm base x of c, plus 3 times the logarithm base x of d, plus the logarithm base x of 2. D. 10 times the logarithm base x of a, plus 5 times the logarithm base x of b, minus the logarithm base x of c, minus 3 times the logarithm base x of d, minus the logarithm base x of 2. E. 2/5 times the logarithm base x of a, plus 1/5 times the logarithm base x of b, minus the logarithm base x of c, minus 3 times the logarithm base x of d, minus the logarithm base x of 2. The correct answer is E. 2/5 times the logarithm base x of a, plus 1/5 times the logarithm base x of b, minus the logarithm base x of c, minus 3 times the logarithm base x of d, minus the logarithm base x of 2. Does this logarithm problem appear intimidating? Quite, right? This complicated-looking problem was modeled on an actual question that appeared on another college entrance test not too long ago. We agree that this problem is several notches more difficult than any of the drill questions we have tackled so far. After covering the basic logarithmic principles, we wish to raise the bar quickly to introduce you to as many of the most commonly used logarithmic identities as possible. This seems to be the perfect problem to accomplish that objective. If you have familiarized yourself with, or better yet even memorized your logarithmic identities, then the solution will come to you naturally and you will be surprised how short and simple it can end up to be. For this particular logarithmic problem, the solution is to progressively rewrite the given logarithmic expression using the various logarithmic identities or relationships. First, recall from the logarithmic identities that logarithm of quantity m over n is equivalent to logarithm of m minus logarithm of n. This is sometimes referred to as the quotient rule. Therefore, we can rewrite the given expression as logarithm base x of the fifth root of a squared b minus the logarithm base x of 2cd cubed. Next, recall that the logarithm of the n root of m can be rewritten as logarithm of m raised to 1 over n. And the logarithm of m times n can be rewritten as the logarithm of m plus the logarithm of n. This is sometimes referred to as the product rule. Therefore, we can rewrite the first term as logarithm base x of a raised to 2/5 plus logarithm base x of b raised to 1/5. Basically the same as the previous logarithmic identity, where the logarithm of m times n is equal to logarithm of m plus logarithm of n. The logarithm of m times n times o is equal to the logarithm of m plus the logarithm of n plus the logarithm of o. This is essentially still the product rule and it applies no matter how many variables are involved. Therefore, we can rewrite the second term as logarithm base x of 2 plus logarithm base x of c plus logarithm base x of d cubed. Next, the logarithm of m raised to n can be rewritten as n logarithm of m. Therefore we can rewrite the logarithm base x of a raised to 2/5 as 2/5 logarithm base x of a. The logarithm base x of b raised to 1/5 as 1/5 logarithm base x of b. And the logarithm base x of d cubed as 3 logarithm base x of d. From this point onward it's essentially just basic algebra. First, distribute the minus sign to the rest of the expressions. The only remaining step is simply to rearrange the terms. And you'll be delighted to find out that the expression we arrived at is exactly as the one in answer choice E. And it's time for another review central pro tip. Memorize the 4 logarithmic identities that we have used in solving our just completed drill problem. If your next mathematics proficiency test will involve logarithmic identities, these are the ones that you will most likely need. 1. The product rule. The logarithm of m times n is equal to the logarithm of m plus the logarithm of n. 2. The quotient rule. The logarithm of m over n is equal to the logarithm of m minus the logarithm of n. 3. The logarithm of m raised to n is equal to n times the logarithm of m. And 4. The logarithm of the nth root of m is equal to the logarithm of m raised to 1 over n. Drill question number 13. Which of the following is equal to logarithm base 6 of 1 over 216? A. Logarithm base 1/5 of 125. B. Logarithm base 4 of 64. C. Logarithm base 1/2 of 1/8. D. Minus logarithm of 3. E. Logarithm base 3 of 1/3. The correct answer is A. Logarithm base 1/5 of 125. The first step of the solution is to simplify the given expression. 216 can be expressed as 6 raised to 3. Hence, the given equation should now read as logarithm base 6 of the quantity 1 over 6 raised to 3. Remember the very first logarithmic identity we introduced in drill question number 9? The logarithm base m of m raised to n is equal to n. This time we are going to use another logarithmic identity, and it is very similar to that. The logarithm base m of 1 over m raised to n is equal to negative n. Therefore, our given expression is actually equal to simply negative 3. Now let's proceed to examine and evaluate each of the given answer choices. Choice A, logarithm base 1/5 of 125. Logarithm base 1/5 can be expressed as logarithm base 5 raised to negative 1. And then, 125 can be expressed as 5 raised to 3. Using our very first logarithmic identity, logarithm base 5 raised to negative 1 of 5 raised to 3 is negative 3. So yes, the expression in answer choice A is equal to our given expression, logarithm base 6 of 1 over 216. Therefore, the correct answer is A. In your math proficiency test you may already choose A as the correct answer, and move on to the next question to conserve precious time. But for now, let's proceed to examine and evaluate the rest of the remaining choices to see how they compare to our given expression, as well as to further review more logarithmic identities. Choice B. 64 can be expressed as 4 raised to 3. Logarithm base 4 of 4 raised to 3 is equal to 3, not minus 3. So nope, the expression in option A is not equal to our given expression. Choice C. Logarithm base 1/2 can be expressed as logarithm base 2 raised to negative 1, and 1 over 8 can be expressed as 1 over 2 raised to 3. The expression will end up as equal to 3. This is not equal to our given expression, so C is not the correct answer. Choice D. Negative logarithm of 3 can be expressed as logarithm 3 raised to negative 1. This can neither be simplified further nor expressed differently, so no, this is not equal to our given expression. Choice E. Logarithm base 3 of 1/3 can be expressed as logarithm base 3 of 3 raised to negative 1, which is further equal to minus 1. This is also not equal to our given expression. In the end, we have established that only the expression in answer choice A is equal to our given expression. There's actually an alternative solution to this problem that does not require us to use logarithmic identities. We can also solve this by using simply our equivalent exponential and logarithmic equations from earlier in our drill. You should be all too familiar with it by now. X raised to y equals z is equivalent to logarithm base x of z equals y. Since our given equation and the answer choices are all in logarithm form, we just need to convert them into their equivalent exponential equations and compare the resulting values of y. Let's start with the given equation. We convert logarithm base 6 of 1 over 216 equals y into 6 raised to y equals 1 over 216. We would quickly figure out that 6 raised to minus 3 will result to 1 over 216. Therefore, y is minus 3. Let's convert each of the answer choices into their exponential forms, starting with choice A. We convert logarithm base 1/5 of 125 into 1/5 raised to y equals 125. 1/5 can be expressed as 5 raised to minus 1. We'll arrive at minus 3 as the value of y, which makes choice A equal to the given equation and therefore, the correct answer. Again, we continue to evaluate the other choices to validate that none of them is equal to the given equation. For choice B, we convert logarithm base 4 of 64 into 4 raised to y equals 64. This should straightforwardly give us the value of y to be 3, not minus 3. For choice C, we convert logarithm base 1/2 of 1/8 into 1/2 raised to y equals 1/8. This should give us the value of y to be 3, not minus 3. For choice D, we convert minus logarithm of 3 into 10 raised to y equals minus 3. Remember that a common logarithm has a default value of 10. This will result to some negative irrational number, not minus 3. For choice E, we convert logarithm base 3 of 1/3 into 3 raised to y equals 1/3, which will give us the value of y to be minus 1, not minus 3. As you can see, both solutions yielded exactly the same values for the given equation as well as the answer choices. Drill question number 14. The expression p times logarithm base c of 3 plus logarithm base c of 2 can be expressed as logarithm base c of 18. What must be the value of p? A. Minus 1. B. 1. C. 3/2. D. 2. E. 3. The correct answer is D. 2. Since the expression p times logarithm base c of 3 plus logarithm base c of 2 can be expressed as logarithm base c of 18, then we can write them as the equation p times logarithm base c of 3 plus logarithm base c of 2 equals logarithm base c of 18. Recalling our logarithmic identities, we can transform and rewrite the expression p logarithm base c of 3 as logarithm base c of 3 raised to p. The resulting two logarithmic expressions on the left side of the equation now have the same base c. Again, recalling our logarithmic identities, we can rewrite them as logarithm base c of the quantity 3 raised to p times 2. The logarithmic expressions on the left and right sides of the equation now have the same base c. Therefore, we can cancel the logarithms. What remains of the equation is now simply 3 raised to p times 2 equals 18. And then on the right side of the equation, we can actually express 18 as 9 times 2. And then we can express 9 as 3 squared. Can you see how both sides of the equation are now almost identical? For our final step, all that remains is to cancel 3 and 2 from both sides of the equation, leaving us with p equals 2. Drill question number 15. A geometric sequence's first term is logarithm base 3 of 64, and its common ratio is logarithm base 3 of x. Find the value of x for which the sum to infinity of the geometric sequence is 3. A. 1/4. B. 2/3. C. 3/4. D. 4/3. E. 3/2. The correct answer is C. 3/4. This is a problem involving a combination of logarithmic expressions and sum of a geometric sequence. Do you still recall your formula for the sum to infinity of a geometric sequence? Here it is. Sum to infinity is equal to the first term, a1, over 1 minus the common ratio, r. The sum to infinity is given as 3. The first term is given as logarithm base 3 of 64. And the common ratio is given as logarithm base 3 of x. Let's plug in the given values into our infinite geometric progression formula, as shown. Using basic algebra, at some point we should arrive at the equation, logarithm base 3 of 64, plus logarithm base 3 of x cubed, is equal to 3. Recalling our logarithmic identities, we know that adding two logarithmic terms with the same base can be expressed as a product. Therefore, our equation now reads as logarithmic base 3 of the product of 64 and x cubed is equal to 3. Again, we recall from our logarithmic identities that we can cancel out the logarithm of a term by raising it to an exponent equal to its logarithmic base. Therefore, if we raise both sides of the equation to the power of 3, we'll end up with 64 times x cubed is equal to 3 cubed. From here we can now proceed to solve for x. We should arrive at 3/4 as the value of x.
Drill question number 16. If a equals logarithm base 2 of 3, and b equals logarithm base 2 of 5, express logarithm base 2 of 3.6 in terms of a and b. A squared minus b plus 1. B, 2a minus b plus 1. C, a squared minus b plus 2. D, 2a minus b plus 2. E, 2a squared minus b plus 1. The correct answer is B, 2a minus b plus 1. Step 1, express 3.6 as 36 over 10, and then as 18 over 5, and then express 18 as 3 squared times 2. Now we have a logarithmic expression involving both a product and a quotient. Step 2, recall our logarithmic identities, specifically the product rule and the quotient rule. We can simultaneously apply the product and quotient rules into logarithm base 2 of the quantity 3 squared times 2 over 5, and express it as logarithm base 2 of 3 squared, plus logarithm base 2 of 2, minus logarithm base 2 of 5. Step 3, recalling the logarithmic identity, n logarithm of m equals logarithm of m raised to n, we can rewrite the first term as 2 logarithm base 2 of 3. Step 4, recall the logarithmic identity, logarithm base m of m raised to n is equal to n. If n is equal to 1, this logarithmic identity will actually read as logarithm base m of m equals 1. Applying this to the middle term, and with a little rearranging, our logarithmic expression should now read as 2 logarithm base 2 of 3, minus logarithm base 2 of 5, plus 1. Step 5, but a equals logarithm base 2 of 3, and b equals logarithm base 2 of 5. Substituting, we should arrive at 2a minus b plus 1.
And here is a summary of the logarithmic identities that we have used in this drill for your quick reference. You may press the pause button to take some time to review this list. You may also take a screenshot of this page if you like. We may post more drills on logarithms and logarithmic identities if and when we've compiled new materials featuring other logarithmic identities that have not been covered here. If you want to learn other logarithmic identities, you may check out some links that we have included in the description below. If you have the time to spare, we do encourage you to learn more logarithmic identities. You'll never know if and when you'll need them in your future mathematics proficiency tests. To wrap up our mathematics proficiency drill on logarithms and logarithmic identities, let's quickly discuss some important notes for you. First, test questions on logarithms and logarithmic identities do not appear on all mathematics proficiency tests. In fact, even when they do appear, they make up a very small percentage of all the questions in the test in which they appear on. In a random sampling of about a dozen previous mathematics tests or subtests that we have inspected, with each test consisting of 50 to 100 questions, approximately half of them do not include questions on logarithms and logarithmic identities. The other half that do include questions on logarithms and logarithmic identities only include one or two such questions in each test. When they do appear, logarithm questions are mostly very basic and simple. But they can also be complicated and quite intimidating, like the last few examples we've covered in this drill, which were modeled on questions that appeared on actual mathematics proficiency tests. You should prepare for the worst. We've seen questions on logarithms and logarithmic identities mostly in the mathematics subtests of college entrance tests or CETs in the Philippines. Among the various CETs, they appear most consistently in the UPCAT, USTET, DCAT, ASET, and the PUPSET. We haven't seen logarithms in many other mathematics exams, but that doesn't mean that it won't appear in future versions of said exams.
You have just watched Review Central's Mathematics Proficiency Reviewer Drills, featuring drill questions on logarithms and logarithmic identities. By now you should be ready to take on any mathematics proficiency test featuring logarithms and logarithmic identities. The drill questions we featured in this particular episode have been carefully curated to present to you as many of the typical logarithm and logarithmic identity questions that appear on mathematics exams. If you wish to watch more Mathematics Proficiency Reviewer drills, check out our Mathematics Proficiency Reviewer Drills playlist. Check out also our other reviewer drill playlists for other topics. If you haven't done so yet, please don't forget to subscribe to Review Central, and click or press the bell button to make sure you get notified whenever we post a new reviewer or other review materials on this channel. Please like if you find this video useful and feel free to share to anyone who may also benefit from it. We wish you all the best on your forthcoming exam.